And with this, let us start, if you don't mind.
They've requested the other company to come down and look at this, or they'll come into the room and that you can decide then if you want to use this or not.
Well, if it's a server for the session, we want to keep it. We
Yeah,
don't want to touch
yeah,
it now.
okay, yeah.
Okay, so please, next slide. So we're on Friday, so if anybody in the room has not seen this slide several times or does not understand it, please raise your hand. Okay, we move on. Next slide. Oh, we do. That's a great question. Please raise your hand. No, joking. So yes, I mean, this is an official IETF meeting. We obey all the IETF rules, which are summarized in this note. In particular, we have a very strong intention of maintaining a good cooperation between work group members. So we insist on the code of conduct and anti-harassment procedures. People have to be courteous with one another in the discussions, whether it's here during the meeting or on the mailing list. We also insist on IPR. If you are aware of any IPR that is new to the group and was not discussed before, either you need to announce the IPR on the discussion or you refrain from proposing the ideas. Next slide, please. Okay, I will leave that for a minute or two. Please read very well. No harassment, be courteous. Good boys. Next slide, please. Okay, now the session is being recorded. Now, there is an automated engine, which we should see on this, which you can see it on the other screen, which is taking our minutes for us, but there are mistakes. So if you can keep an eye sometimes on it and make sure that what we are saying is being captured properly, that would be nice. And then we have ESCO helping us taking the minutes. So if you see ESCO, we trust you. If you see something wrong in those captures, please keep a small note on it. You'll find on the agenda page all the links to the note-taking tools. Next slide. Okay, and these are the resources for this IETF. Well, the screen doesn't work, but we can't interrupt ourselves, so we'll continue if you don't mind trying, but we'll just continue. Next slide, please. Okay, so we have published an agenda, and during the normal period, we have a slight change that we will show you on this agenda. So for today, we'll start with this opening that's happening now. We'll have Laurent Toutain presenting us the status of the ICMPv6 draft. Then Alexander will propose the new discuss the new version of the FAQ draft. There was a FAQ draft earlier, which was kind of stalled. We really insist on forward error correction in SCHC. That's a very interesting and important feature for us. And now that we are considering SCHC over space, it becomes even more interesting for us to work on SCHC, on FAQ for SCHC. So Alex will present that to us. Then we have Marco giving us an update. Marco, thank you for coming, giving us an update on the SCHC CoAP draft update. Next slide, please. And thank you, Mark, for being with us. So there was a lot of activity around deep space. So we must be Deep Space 9 by now. So Mark will give us a status of the discussion that happened during this week. So thank you, Mark, for this. And in particular, we are interested in possible action items that could be brought into this working group to support the deep space activities at the IETF if the working group is effectively started. And even if it's not, actually, if there are good use cases for us to work on. Then we'll have Then we'll have the discussion on the low power zero energy devices that Edgar and Anna have started for a while. So we'll have a status on this draft. And as you know, we have changed the name of the draft from zero energy device to disruptible networks. And then that's the change that we just made in the agenda. We wanted to discuss a little bit the terminology, but we are not really ready for that. So the authors decided to kind of not do it, wait for the next IETF, and we'll have a bigger session dedicated to architecture and terminology when we feel more ready than we are now. Let's discuss on the mailing list till then. And instead, we are lucky to have Mariam Atami presenting us work which has happened about using basically SCHC and Brusky together. So Brusky is the security exchange that enables autonomic networks. It's a three-party game. So Mariam will explain how they have implemented a solution that combines SCHC and Brusky. And then we'll have this new concept of a SCHC action, which is kind of a spin-off of the ICM PV6 work, and that will be presented by Anna. And then hopefully by the time of the end of the official meeting, we'll be in AOB time. Okay, so status of the drafts. So Marco has published a new 8825 update. We have also a new ICM PV6 compression by Laurent published. The architecture is a bit stalled. It's expired, but we are working actively on it. We just did not feel that there was stable enough changes that we could republish architecture 3. So we are on it, but we expect to publish 3. Protocol numbers, I will give you a status after those slides, so let me delay that. Other expired draft, as you know, SCHC over PPP, the idea is to wait for the architecture to continue working on it. So it's not progressing, but it's voluntary, it's under control. SCHC access control, maybe Laurent, do you have a word about SCHC access control?
Yes, for the moment is also blocked because due to the architecture draft, and I think so when we will have the architecture, we will have a clear vision of what we want to do on this, and then we can go on it.
Okay, so and now the new drafts. So basically, nothing. I don't need it. Okay, so we've got the new version of the FAQ work, but which is really a restart or a kickback on the FAQ work. And that's what Alex will present us in this agenda. And the entire protocol number still shows, but it's replaced by the SCHC protocol numbers that I will discuss right after the slides. Next slide, please. Laurent, do you mind coming to the mic?
Yes, so we are happy to announce that we have now some tutorial material about SCHC. So we have a web page that the name has disappeared here. It's vm.openschc.net, and here you have access point to different elements. So VM because you have a virtual machine that allows you to test some SCHC element around OpenSCHC. And you have also access to the book of SCHC. We are here in the book of Kel, but we have the book of SCHC, and it's a tutorial also to you to understand SCHC and to make some exercise on the virtual machine. We have also videos. So these videos are in the third button, and you can access to a lot of tutorial teaching material about SCHC. And normally, we should have open a MOOC during the IETF session, but we have some unexpected delay. But during the month, this MOOC will be open. And did you put the next slide? Did you? And for the video, if you want, you even can hear Anna singing disco in this video.
It's actually a very beautiful video. It's well made and very explanatory. I love it. So I really encourage you guys to go to the link, which is on the top left of the slide, video openschc.net. They're really they're coming from an expert teacher, and they are really good at telling you rapidly how all our stuff works. So I really love those videos. Yes. So and now, as I promised, we have this discussion about the SCHC protocol number draft. So it's a draft which is supposed to be very simple. It has to be very simple. It's pretty much a spin-off of the architecture, just to be asking for an IP protocol number and an ether type through IETF to IEEE. And that's it. That's what this document is for. Now, we had also a section asking for UDP port. And as the earlier reviews both mentioned, we were not ready for that for a number of reasons. One of them is we don't have a clear use case for it. And even the flow that would be used to use that dedicated port was unclear. It might very well be that the SCHC instance is started by some control somewhere, which tells us which ports to use, or the ports have negotiated without needing first a SCHC port. So we don't, at the moment, really need that UDP. So we decided, hey, let's drop that piece. Well, that's a proposal on the table, unless somebody has a real need for it. But we are not aware, the authors are not aware of a real need for the UDP port. So we propose here to just drop that section and ask for only the IP protocol number and the ether type, which will basically solve Eric's problem as well, which is the sections were TBD. Yeah, they were. So there was also, Mireille also raised the question that this should be part of the SCHC architecture. I mean, the SCHC architecture should just have one section asking for an ether type, one section asking for an IP protocol number. I have problems with that because the architecture will take a long time. And then if we have to delay even more to get the port numbers and, well, not the port numbers now, the ether type and the IP protocol number, that's just extra delay that we don't want. So I'm happy with this normative reference to the architecture, which is also on the table. And let this thing become RFC with the normative. Well, no, that would stall till the architecture is done. I would be happy with an informational reference, but not with normative reference because the RFC would be stalled unless the pending RFC is enough to ask for those numbers.
Eric Ving, the responsibility for this working group. I was about to jump to the queue on this.
Yeah.
Most probably you can have an early allocation. A working group adopted draft is enough, fairly enough.
Even to go through to IEEE as well?
To IEEE, I'm sure on this one.
Okay, I mean, I'd be happy to ask for early allocation. Now, it's not easy to get an IP protocol number. There's not so many of them. Well, okay, you think it's going to pass? No. Okay, that's great news. I was a bit anxious on that side. Okay, so that's ether type star 2 bytes, so it's more.
So Eric Ving again, just to be to be sure for the remote people, because I said yes with my head, which is not, of course, going through the the audio. So yes, it's kind of easy to get an IP protocol number. We did it 2 weeks ago for a protocol which is not even really used yet. So
compared to SCHC, which is broadly used.
Yes, exactly.
We agree on that piece. Okay, and I think that's the last slide. So can you just, so Laurent, I believe you're next.
Okay, so I will talk about some.
Laurent,
Yeah.
So regarding Joe touch point that we do not need an IP protocol number, for the summary it was on the slide, I don't agree with him, right? Even if we have only SCHC between two IP addresses, we still need to get what's inside and next. That's for sure that was the summary, right?
Yeah, Joe challenged IP and rejected UDP with good reasons, like what's your flow? You're supposed to talk to a service, not to talk to another peer through that port. And yes, that would have been to negotiate the instance, not to establish the instance, just how you say, hey, I want to create an instance with you. But we don't have that flow in the architecture. We are not ready asking for it. We're not even sure we're going to provision our instances like this. So that's why, yes, UDP, we can put it aside. For IP, said something, that's when you do IP in IP or something, and it really lost me. I mean, the text that Joe wrote, I could not parse it. Maybe you could.
I don't know. I will.
But the way I read it, he said it's like we are using. I think he understood that we wanted to do IP in IP, and in the inner IP we would do the compression of the IP header. No, it's not what we plan to do, right? We want to compress everything after the IP header, not another IP header inside the first IP header. But that's how I read Joe's text. So I think he was basically, I did not really consider that comment.
And the last one, the use case for UDP is typically as well to cross NAT device.
Okay, so both Miria and Joe, they said that's not the recommended way for doing it. So I would not have used that. Yes, that's why we wanted to do it. but from their command coming, Joe from TSE area and blah, saying, well, that's not the right thing to do. And Miria security saying that's not how you cross nets. I was like, wow, maybe I won't insist that on being the major reason why I want to do this. Because if those two guys tell me it's a bad idea, maybe I should listen. So we're not ready. We're not ready for UDP. Let's not delay IP and Ether type.
Okay, so let's go back to this draft, which now is a working group draft. So it comes from the OAM world, but since we are focusing only on ICMP V6 compression, so we change the name to be more explicit. And the co-author is Dominic Barta. Next slide, please. Okay, so as I say, we change the name. There is still a mistake in the young data model, but or continue to reference OM, so we will change it soon. So it has to be also aligned on the architecture document regarding some vocabulary, but I think it's not so important. And the draft has been divided in two parts, so generic ICMP VX6 compression, and then the second part where we have the optimization for constrained device that are not only in the device part, but also in the network gateway part. So next slide, please. So what we do for ICMP generic compression is that we have defined different fields. So we have the one that you have in every ICMP header. It's the type, the code, and the checksum. And then for each field that have been described in RFC 4443, we have also a field, it's identifier, sequence, pointer, and MTU. What is important to notice, and it's in the SCHC philosophy, is that we don't have something for the unused field that appears in the ICMP description, because it's just padding, it's not information, so we don't have to put it in as a field. And what is also important is that since ICMP is a stop protocol, there is nothing on top of ICMP, so we have also a field that covers the payload of ICMP message, and that will be useful in some scenarios. So next slide, please. So then if you want, I can go into details, but it gives some different scenario on the use. So you have this example in the draft, so that explain how you do the compression of different ICMP messages. For here, I give an example for destination reachable, and you can see how it works. Next slide. Okay, so what we introduce also is something that is a packet too big, so that can be sent by the network gateway when, for example, you want to reach the device, and the device is you don't have a rule that allows you to send, with a fragmentation rule that doesn't allow you to send this information. So here the network gateway can generate an ICMP message saying that the packet is too big for compression. So next slide. So normally, so here we have the ping compression. So it's something regular. So you can compress different fields. You can, of course, it's not the rule you can use all the time, but you can ignore the identifier if your device is just sending one ping at a time, or you can have something larger if you want. Same thing for the sequence. You can reduce the size if you don't send too much messages. So it depends on the traffic. Yes.
Pascal Charatov, just to mention that there is work at SIXMAN about a more generic echo function, like you send something to the other guy and the other guy sends back what it sees, and it's mostly for traversing NATs and stuff like that, so you can see what the other side sees. The workgroup adoption was added, asked. I don't know if it's going to happen, but it's an interesting feature, and just let's monitor it, because if it progresses at SIXMAN, maybe we should look at it as well. So it's
Okay.
a more generic ping, if you like.
Mm.
But I think it will be interesting for our networks. And also we may want to decide, hey, do we want to send that to the peer, the device, and then the device would echo the compressed thing? Because we never get to see the compressed version of the packets otherwise. But with this new feature, we could say, hey, if we go all the way to the device, then the device echoes the compressed version of that he got. And if something fails, that could be useful.
Okay, so we can see that. So we can add. So for the moment, we do not change the ICMP. We just use the regular one. We have no new features. So it's just the way you do the compression that can be a little bit different regarding this ICMP. But maybe it's good. It's interesting to have some other debugging mechanisms. Yes. Okay, next slide. So yes, so now we go to the second part where you have constrained devices. So our goal is to try to remove some traffic from the constrained device and do things in the network gateway when it's possible, because ping is not encrypted. It's a message that is quite light, so we have access to a lot of information at the gateway. So next slide. So here we have something that say, for example, you want to send a compressed packet. It arrives through the SCHC core, so we have now to call it network gateway in the new vocabulary. But so you don't find a rule for different reasons, and so you can inform the source that your packet will never reach the device because, for example, the port number is not defined on the device. So it's stupid to send information because we know that the device will not be able to answer with this port number. It's something for different cases, and I copy here from the draft the different case when you can generate an ICMP message. Next slide. So on the other one that is a little bit more tricky is that, for example, the device is sending something on the network, and then the packet doesn't reach the destination. And then so an ICMP message will be generated by the network, and it has to reach again the device to inform that it's stupid to send things because its packet doesn't go to destination. So save your battery and wait until it's repaired. So here we introduce two new matching operator. In fact, we are using only one in this draft, but since for symmetry, we introduce the two, and also two CDA, so for compression. So the matching operator, in fact, the goal is when the packets come back, ICMP message come back, it contains the IP packet that has generated the header. So we can do again the compression to send the compressed things to the device. So the matching operator say, hey, look at the payload. So as we see now, the payload is a field for ICMP. And do you find a rule that match this payload? So in the other direction, because here you have a up message, and when it comes back, it's a down, but it has to be viewed as a up messages because it was the other way. So so that's why we are reverse rule match. So if you find a rule in your set of rules that match this packet, so the incoming packet, so we can do some action. And same thing, so the action will be, for example, to compress the payload again to not send the full packet to the device. Okay, next, I think it's, so here you have the explanation, so I skip it. And so what we remove from the draft is action. So it's something we have to discuss. Anna at the end will discuss about it. It's something that asks, so we can go to the next slide. When we have, so an action is activated when you have a rule that is selected. So it means that it matches a packet that arrived and has been chosen as the rule to do the compression. And so we can trigger a procedure that will do some things on the packet or around. So for us, it's to have a proxy ping. So to answer in behalf of the device, because the SCHC gateway may know that the device is active because it see already some traffic in the 5 last minute, for example, but it's a value you can put in the rule. In the last 5 minutes, I saw traffic, so I answer to the ping. If I don't see any traffic from the device in these minutes, in more than 5 minutes, so I don't answer to the ping. So it's very cheap for the device, and it's a way to see if the device is active. So that's why we created for that, but it can be generalized to other things like so the flow compression that Anna will present at the end. Okay, I think it's. So no, so the question is, but it's for the end of the discussion. We have to define action and to in the architecture document and also in another RFC.
Questions for this presentation? Okay, so Marco, we move on if you don't mind. Right, oh, pardon, sorry.
Can you try starting sharing the slides?
Lost it.
Okay.
It's just a display. It's just a display, it's not in control. It was Marco. Oh, it's like 20 minutes?
Yes. And you need to change the
I will. Attends, tu veux pas. Ça, tu prends pas là? Chez toi?
No.
Okay.
I'm really sorry for you, Pascal. It doesn't work, and you'll have a lot of changes to do.
Press the button.
Yeah, you can press the button, but you'll see there are a lot of buttons. So thank you very much. I'm going to be presenting. So if you can go just back one slide, because so this is a work. There are several authors right now. So we have Alejandro, who is not here with us today, but he's working a lot on this from IMT Atlantic. Kui from Actility, and then we have a new author, Martin Eus from University Grenoble-Alpes, and me as a co-author for this work. So next slide, please. So the idea, of course, is to define how FEC could be added to SCHC. So I'm not going to go into a lot of details, but one of the reasons is, of course, that we want to save downlinks, right? Whenever we apply fragmentation, we can send some additional frames, some additional fragments, or some additional data, and this will hopefully limit the number of required downlinks. And we have a very specific use case. So there is a big smart gas meter deployment happening in Italy. So it's the Italgas company, and they're rolling 7.5 million smart gas meters in Italy and in Greece. Like it's dually connected, and you have a LoRaWAN interface there, and of course, like it's working as of today. But it will be really good if we can add some functionality that will limit even more the number of required downlinks. Next slide, please. So yes, basically this is what I said, and there is a slight change since the last time we presented the draft. So right now we have added an additional FEC mode. So the first mode that we presented in the last time, it's not exactly that, but I'm going to just for you to illustrate, we call it ships in the night. So and the second one is FEC before frag. Okay, all the names can be changed, like this will be discussed, but so next slide, please. So the ships in the night mode, and this is what we used to call, this is the SCHC FEC fragment rule format. So basically it's defining a new rule format, right? And it is a specific type of PDUs that only contain the FEC information, and they use a separate rule ID, so they're completely separated from the fragmentation process. Let's say they can be completely isolated. And so the baseline, the idea is that you have a baseline fragmentation, and this fragmentation is like it's working as it's always been working, and then you define an additional process, let's say, with a different rule ID. And whenever you send SCHC PDUs with this rule ID, well, the receiver uses this information to complete, eventually to recover missing information that was normally sent in the fragmentation process. Next slide, please. So we have the data. This is the SCHC fragmentation. It has the buffers that it's using for that. Next slide, please. So this is the normal fragmentation process. Like, it sends fragments to the reassembly, and it uses some local buffers, and then the data is sent to the upper process. So that normally does the SCHC compression that's above, right? You have SCHC compression, the compressed data is sent to the fragmentation, fragments. Next slide. And here what you have, like in the ship in the night, is you can have this separate process that's basically sending FEC fragments from time to time, and that is calculating this FEC based on the initial data here, and it's allowing to recover this data so that the reassembly process can be really unchanged. The fragmentation and the reassembly can be unchanged. So I have a couple of examples. Maybe you can give me the computer, because otherwise I'm going to be saying next slide every 30 seconds. Maybe I can sit. Oh, okay, let's do it like this. Okay. So we have the data. The data is split in tiles. So this is the data coming from the process above, before the fragmentation, right? Then it is split in tiles. So here the numbers are just for the example, right? Like, you imagine that we have a big number of tiles. So normally what we have is that these tiles are put in fragments. So each of these fragments is sent, right, and then received by the receiver, and on the other goes in the other way. Now the way this ships in the night model works is, well, we have the fragmentation. We have the fragmentation with rule ID 20, let's say, and then you have like a secondary process that operates on a FEC window. So it's specified in number of tiles. So this FEC process, typically in the example that we use, is like it's the size of 2 fragments. So you apply this FEC process, and this gives you a new fragment that you can send, and it's sent on a different rule ID. So the receiver, when they receive this, if they don't support that thing, like they don't support rule ID 30, they can simply ignore that. Like, nothing is broken there. And then your fragmentation process continues. So you put fragments, you put your tiles in the fragments, you send them, and then an additional FEC fragment is sent. And so the receiver, in case some of the fragments are lost in process, can use this FEC information to recover the lost tiles. So that goes on. A little bit ugly here, but here is an example how it works in case the MTU changes. So it works in case the MTU changes dynamically. So you have here the same operation with MTU equals 5 tiles, and the FEC window is 10 tiles. So this is as what we saw until now. Then at some point, because the radio conditions change, maybe you have your fragments that become 3 tiles. Now they are smaller, but yet again, like your FEC window also changes, so it becomes smaller as well, and your FEC fragment is sent, and it covers, the 2 previous fragments. So every time, because basically you're limited, if your MTU changes, also your FEC fragments, so the fragments that carry the FEC information, they also need to be reduced, right? So you need to diminish the information you can send. So this continues on and on. I'm not going to go into lots of details. So a couple of examples here. FEC fragments can be sent at any time. So you can say, for example, hey, well, I have my 2 first fragments, then I have a FEC fragment, then another fragment of data, and then another fragment with fake information, and this way you can have like it's defined on a like on basically you have in the format you have a pointer that says, well, I am calculating the fake based on the previous n tiles, right? And you can send it at any time, and yeah, so this actually provides a lot of operational flexibility, depending on your deployment, right? And here we have not changed the fragmentation at all. Like everything that we've been doing until now, it's valid, and it's a very simple process to add this fake mode of operation. I have 5 minutes. Okay. You want to ask a question? Okay. Yes, please.
So just a remark that this appears pretty much like a very simple way of doing what we generally call network coding. And we have work at the .NET working group where we use multipathing along a direct acyclic graph to go from point A to point B to add diversity in transmission, spatial diversity, time diversity, etc. And this improves the chances of the packet going from A to B. We mentioned in the row architecture, we mentioned network coding as a good complement for the row activity, which happens in the routing space. So it appears that with a support like this, SCHC would become a good complement for the row architecture and for using row on a network, because it would be an IETF way of doing a simple network coding that would enable to flood the graph.
Thank you, Pascal. And just so that you get like this in your idea, like the first example and the example that we're using in the draft is with XOR. So that's like super simple, right? There are other ways to do FEC, but this is like the layer one, and it's super simple. So I'm continuing with some other examples. So how does it work? Okay, so this is a very artificial example. I would advise anyone against doing that, but you can do that. You can have, for example, you can define that your FEC window is less than 2 times the MTU tiles, for example. So basically, you're covering tiles from 90. The first fragment, the first FEC fragment there is covering tiles from 97 to 90, but basically they're sent in fragment 1 and 2. So basically, if you lose fragment 2 and only get fragment 1, you'll be unable to recover fragment 2 from that. Like it's a stupid example, right? But just to say that these are decorrelated, like it's really a parameter of your FEC fragment. Another thing that you can use actually, and this is more interesting then, is that you can add additional ships in the night. Like you can have your FEC fragment or rule ID 30 with some parameters, and another one with rule ID 40, let's say. They're both anchored in the fragmentation session that goes with rule ID 20, and they're both helping to recover missed pieces of information for this ongoing fragmentation session. And here you can play with parameters. Like this, of course, is very important for operational deployment. Like the operator can deploy devices, and depending on the network conditions, they can say, well, here I'm going to activate this kind of FEC fragments with this window size, with this FEC window, and with this frequency of sending. Yes, Eric?
Eric, just clarification questions. I wonder why you are computing the 99.78 based on the original tiles and not above on the fragments. I mean, the fragments by the rule 30. Because then you can recover easily one of those FEC fragments.
Okay, so it's for in this case, it's for simplicity, like basically allowing for operational people to say, well, I'm adding things, and because I'm very good in math, I calculated by doing this, I have the necessary level of redundancy. Probably you can do that as well. Karsten?
Sorry, I didn't press the hand. Generally, you're using codes here that allow you to reconstruct from any FEC fragment you get. So you don't have to protect a FEC fragment. You're protecting the original exchange. So I don't think that would be needed.
Yeah, I mean, a question to look for. So, okay, So as you see, like so this was like the ship in the night mode. So I'll go to the pros and cons at the end. But one of the pros is that it can be very simple to implement, right? And it's backward compatible. Now the other way of doing that is do FEC. So apply a FEC algorithm and then apply the standard fragmentation. Like in this case, we don't change anything as well to the fragmentation, except that we need to indicate in some way to the fragmentation that, hey, well, you don't need to recover 100% of the fragments. So even if you recover 70%, let's say, of the fragments, it's okay because the data inside that you have, it's data plus FEC. So you can put it to the upper layer and then it will actually recover the full data, right? So there is a slight addition that needs to be done to the fragment, to existing fragmentation. Okay, I have 5 minutes, okay. And there is a small question of how do we actually integrate this in the bigger picture of SCHC, because if it comes from the upper layers, normally it's a compression. There was a SCHC compression before that, so we can say, okay, this is a SCHC. There's a SCHC compression, and the action, the CDA. So we add a new CDA. The action actually does FEC, calculates the FEC, and the output of that is given to the fragmentation, right? But then if you want to do compression before that, you would like to do SCHC compression, which will do the compression, then send it to another SCHC compression, which will actually do the FEC, and then send it to the fragmentation. So there is an architectural discussion. How should that be done, if that's the way? So this is the example here. This is what I said. So you have the data sent to the fragmentation and then recovered on the other side. And even if you have missing pieces, it's okay, because like you have a parameter, and here you can have a very, like, there are many FEC algorithms that are in the literature. So you use any of them and it will work. Okay, so this is what I said here. And probably just, I think I'm almost at the end of my presentation. So the pros and cons, and why I think that probably we'll end up having both fragmentations, both FEC modes in the end, is so for the ships in the night, so it's backward compatible. It's very simple to implement with a small caveat that you're probably going to touch shared memory on the processes, so that needs to be done carefully. And there is less buffer space to be used for sender and receiver. I'll tell you why about this. It's quite flexible, but also I think that we need to provide the guidelines, like to say, well, if you want a very simple thing that works 90% of the time, like just every second, every 2 fragments that you send, well, send a FEC fragment, like, and you XOR of that, and that's it. Like I think that will cover maybe 80% of the cases. If you want something more advanced, well, like you need to roll your sleeves and write exactly what's happening, right? So what we need to do now, probably we need to look at other FECs other than XOR, but I'm not sure about this. And whenever MTU changes right now, what we say is, well, basically, just restart the process. Like it's too complicated to try to signal to the other and something like just start counting your fragments from 0, and it works like this. Okay, so these are on the ships in the night. FEC before frag, it can be much easier to get random or like a random FEC algorithm to be working with in this way. Like we don't have to look at every fragment. I mean, I think it's going to be easier. And no need for FEC fragment emission strategy. Like you don't have to count the fragments to say, okay, I've sent 1 fragment, second fragment of data. Now I have to send the FEC fragment that contains the fragment. It's all mixed up. So just, run number fragmentation. I think that one thing that's really going to be a penalty by using this mode for constrained devices is that probably that you will need an additional RAM for a bigger buffer. Because when you have your input data, you have your data, then you need to run the FEC on that, and it will generate like a buffer with a bigger data, right? So that you can send that to the fragmentation process. And that buffer is going to be, let's say, if you need to be sending 1,280 bytes of data, the buffer will be, if let's say 60% bigger, because your FEC is going to generate 60% more information. So you'll need like a 2K buffer at least that is going to be used only for that 2K RAM, and that for embedded devices can be suboptimal. And yeah, we have some work to do. And but things are going on, of course. And if you are willing to help, and if we're interested in that, we will be pretty. Uh, we'll be glad to work with you.
Je peux préparer le jet là-dessus. Ah non, questions.
So if you go back to the previous slide, for me, these are two faces of the same thing, because it's when you have a XOR is 2 message over 3 and another one is X message over Y. So maybe there is a convergence that can be done, and you will have a single way to process these two modes.
About the memory.
Not the memory, the process. It means that you XOR and another more complex thing is, in fact, if I have, in the first one is, if I have received 2 fragments over 3, I am happy. And I think I put a 1 in all the, no, because you're in another one. But for the other one, if I receive 3 over 5, let's say, then I hack the 5 messages.
Okay, thank you.
Everything out of curiosity, again, do you have numbers and measurement? How many fragments are lost in a row? Because what I heard sometimes over some kind of wireless transmission, it's multiple milliseconds or seconds.
Okay, so yeah, thank you for that question. Well, actually, there are 2 points here. The first point is that sometimes it can be a lot. Yeah, it can be like 30% loss or something like. So basically we need to protect against that. The point is that what we want is to have a parameter, so that can be a question for the operator. Like the operator can deploy devices, and they can say, well, for these devices, I'm not using that, because they're like it's good enough as it is. But hey, I have these other meters that are very far away, and I have a lot of losses, so I'm going to put the redundancy to 1/2 or 2/3 or something, and then it runs in.
But it's not so much the packet error rate that I'm concerned. There's the numbers of packets that are lost in a single bad event.
Okay.
But then you cannot recover, right?
Yes, in a burst.
Yeah.
Well, I mean, you should be able to recover if you say correctly. So it's yeah, if you lose like 5 consecutive packets, and your thing is protecting against 2 losses, well, it's not working, right? But if you are saying, okay, well, yeah, I mean, yeah, I get your point. We need
Anyway,
to.
I was just wondering whether you get measurement to see whether it will be very
Yeah.
useful or marginally useful.
Yes. Yes.
Yes, the moment. So you have this item, no need for fake fragment emission strategy. I would change this into no opportunity for fake fragment emission strategy and put it under the cons. So I haven't read the draft, but from your presentation, I think this is totally useless. The
Totally. Sorry?
alternative is totally useless.
Which one? This one?
Yeah, you should not do that.
Okay.
Just another alternative, another interoperability headache. Just focus on
the first one. Okay. Okay. Thank you.
Support that too.
Okay. Pascal supports that too. Okay. Thank you. Ivo comes to the mic.
Ivo Petrov, have you considered running some simulations? How much that will help, basically?
Yeah. So we will have to do that. One of the points is there was a research paper actually that was that they did a lot of analysis, and they in the end they came up with, well, like doing XOR of 2 fragments is good enough. Like you have 90% or something. So I read that paper and I was like, okay, we need to do that, and then we'll figure out how it works. But you're right, like it. So this is why it's actually quite interesting that they're decoupled. So if we see that, hey, well, it's not, the redundancy is not enough, we can just send more fragments, right? But yeah, I mean, in the end, if the data is really important for you, you still have the fragmentation running. and the fragmentation is going to recover everything that's been missing, right? The point is that you can optimize, but yeah, we need to do some. Actually, we wanted to implement it and run it, but yeah.
Yeah,
Okay.
so just to remind people, why would we use FEC in the first place? There are two reasons to use FEC. One is multicast, so the same message is received by multiple receivers who actually lose different fragments, so they benefit from a single correction, from a single fill-in. The other reason is that you don't want to wait for something like negative acknowledgements, or you don't even have an opportunity for negative acknowledgements. Then sending FEC improves the situation because you don't have this additional round trip, or you don't lose the packet. So you're not using FEC indiscriminately. You look at these reasons, and if none of them applies, do retransmission.
I guess I'm next. No? Yes, I'm next.
Yes.
So I want to react to both what Carsten said and what Eric said. There is actually a third reason for using FEC as soon as you're operating on a graph as opposed to a point-to-point, which is to use it as network coding, in which case you flood the network with your FEC, more or less. I mean, you send some fragments to left, some fragments to right. They use different paths, and one of those paths may be interrupted for effectively split second, 2 seconds. I mean, that's radio. And this is when using the alternate path and using FEC over all those paths and flooding this graph basically with not all FEC elements everywhere, but a subset through different paths. So you're adding diversity to diversity, diversity, space diversity, time diversity, etc., even technology diversity. That's when you end up in the end receiving enough fragments or FEC fragments to reconstruct, even if there are temporary losses here, there. No? So if you think about it as a point-to-point, yes, I mean, a few seconds of loss will kill you. But you think of it as a network coding over a graph, now you can still survive.
Thank you. Laurent?
Okay, yeah, for the applicability statement, if you focus it only to electric meter, I think an XOR can be enough. But if you say we are going also to the deep space scenarios, then maybe we need stronger FEC. So it's something that has been to be precise.
Okay. Thank you. Okay.
Okay, it's time. We're past our time actually. So we're a little bit late, but that's okay. We are a bit late, but those were really interesting questions, interesting discussions, and that's why we're here. So
okay, hi everyone, this is Marco. This is an update on the working group document on SCHC for compressing co-op headers, now in version 3. Next slide, please. Okay, and the goal is not changed. It's still about obsoleting RFC 8824. So we have the same scope really. And fundamentally, there's no core change on the mechanics on using SCHC for compressing co-op headers really, but still, there's a lot of clarifications on different areas that were covered in RFC 8824. More details also on the compression of co-op options, current ones, and recent ones that were introduced after RFC 8824. The biggest part of the document is actually being explicit on how compression happens in the presence of co-op proxies, with or without OSCORE, and with a lot of examples. And in the previous version, we introduced also new IANA registry, basically to keep track of the header fields for co-op and especially options, and they are introduced with the ultimate goal to stop updating this sort of document, at least for that reason, in the future. It should really finish here. And well, we also have a young data model that we keep consistent as an extension of the one introduced in 9363. Next slide, please. Okay, this is what I wanted to talk about, just an overview of the update of this latest version. An open point I noticed and I wanted to mention and discuss, maybe time doesn't allow to cover the comments from Quentin and the thoughts that the authors put on that, but I'll try to be fast if I have to stick with the minutes allowed. And then, yeah, summary of next steps. Next slide, please. Okay, since the last version, I put a relative editorial effort in improving a few things. I noticed that the same thing in principle was stated in slightly different ways in different sections, so now it should be a bit more consistent. In the example rules, co-op version was indicated sometimes as 0, 1, sometimes with 1. It should really be 1, and now it's 1 everywhere and consistent with that. And I noticed that the unit byte or bit was missing in the variable and field of the example rules when we used value central as B. Now it's present there, consistent with the intention of the example. Karsten.
There is this standard ISO IC 80,000 part 3 that tells you that a byte is abbreviated O for octet, but you can also use it in uppercase B, and a bit is abbreviated bit, because we don't want to rely just on uppercase, lowercase distinction. Please use bit whenever you need to abbreviate bit. Thank you.
Point taken. I'll double check. I had the impression that 8724 was doing that, but thanks.
Yeah, that's right.
Ratum on the way. Thank you. Okay, we used to have in the previous section a single section covering two fields of the co-op header, the token length field TKL and the actual token, and they sort of discussed together a bit back and forth even, I think. So I took the liberty to split that into two different sections, and as a side effect, now if you check the table of contents, now we have as many sections as the number of co-op header fields, exactly in the same order, so it should be really straightforward to read with a clear separation. And once I was working on the new token length field subsection, I noticed, yeah, it has always made sense to focus on two practical ways to compress that. Why not considering also the case where MO is match mapping? Yes, it's quite unlikely that you can really take advantage of that, but I don't see the way to exclude it altogether either. Next slide, please. Okay, and I had some discussion again offline with Laurent about this particular entry in an example that was fixed already to address an erratum, and the fix was still consistent anyway, no doubt about it. But the example still looked a bit ambiguous for two reasons. You already have the field position entry telling 1 to state clearly we are talking about the first occurrence of the URI path option. And the value field here could be probably misinterpreted as something that has to match with the URI path of a honestly very weird co-op request that can be sent. So rather than trying to explain what we really mean here, that can be even more confusing, we concluded at least to transform the example at least as to the value entry into something very simple, like just any other example in the document. And at least that there shouldn't be any confusion anymore. But then even on the back of someone's hand, there's the intent of introducing a sort of wildcard. Well, there's something more general that I don't think should be really proposed in this document, at least. So now this example is consistent with the others. Thanks. Right. I found, I think, a mistake in some examples where OSCOR is used, and one of those mistakes was, I believe, already present in 8824. With the rules we are considering, we are compressing with LSB one of the field of the, two fields of the OSCOR option, the partial V and the KD. And if we do that per 8724, we are supposed to put on the wire prepended the sheet compressed length of the residue that is sent of the wire, and that was not in the examples. So I fixed the examples to be consistent with that. Two examples were new because they were based on proxy. One was inherited from 8824. That's also fixed. Question here is, should I file an erratum against 8824 about the wrong example there, or we skip it and we leave with the fix already coming in this document? Any opinion on that? I won't do it. Okay, next, please. Yeah, okay, we have security considerations on the Young data model. I put some thought about it. It seems to me we can just inherit those that were defined in 9363, because here we're just extending the same data model with some more nodes. I don't see anything radical or considerable to add to that. So if there's no particular input, we can probably leave just with the sentence I'm quoting at the end of the slide that is already in the document. Okay, next please. Yeah, this is my open point. We are already compressing the total field in a smart way to avoid confusion and to reduce overhead on the wire. And we are avoiding the inclusion of the wire of the prepended length of the residue based on the length function TKL. And consistent with that, we are using the same trick for other fields of the Oscar option. All good. I noticed that for some reason, 8824 is not doing that for another field where this is in principle possible, the partial AV of the Oscar option. And you can easily introduce exactly with the same motivation, a simple function OSCPIV that would look at the last 3 bits of the first byte of the Oscar option. And that's basically the length of the partial AV field. And by the same means, we avoid confusion. We spare overhead on the wire, roughly 4 bits, I think. And so on. So yeah, there will be, if you want, a feature introduced as a new thing compared to 8824, but I think it's worth doing that for consistency and for performance reason. So I plan to add some proposed text to the next version. I see Laurent nodding. That's a good sign. Next slide, please. Okay, we maybe don't have time to go through this.
Mailing list, please. I mean,
Right.
these are big discussions, and,
Yeah.
and we are at, you have 1 more or 2 more minutes, but
That's okay. That's a minor clarification that is pretty uncontroversial to do. The big things seem that the authors agreed to not make this big change at least. So more input from the working group is welcome, of course. And yeah, we'll prepare a reply to Quentin anyway. Thank you.
thank you very much.
That's all I had.
Any question? And then I guess we are going to deep space.
Just one thing. Thank you for actually taking the time to address all the questions that were asked on the mailing list by Quentin, and probably yes, we can go over these things during an interim if there is
Yeah.
a need for that. But it's already documented in your slide, and probably can send an
I'll
email.
put the slide into a mail, yes.
Yes.
And please have a look on the GitHub if it's possible to transfer the sources of this draft from my personal repo to the LP1 repo.
Oh, okay.
I'm still lost in it. I can live with it, but I don't think it's super appropriate.
Oh,
Okay.
yes.
Yeah.
Thank you
okay.
very much.
Thank you.
So I'll be doing this. And with this, we invite Marc Blanchet. So Marc, thank you so much for coming with us. You need your slides here? No.
Just
Okay.
a few notes.
Okay. Okay.
The co-chairs asked me to, present you what we've been doing for deep space, and especially kind of a few topics related to your group. You said we're going to deep space. I'm not going to deep space. Me, my children. Next slide. So I just did some slides yesterday based on your request. Happy to answer any question. Hopefully that's relevant to what we're looking for in terms of information. So deep space communications, there's roughly 2 things that may matters. Delays. So Earth to Mars, 5 to 20 minutes, one-way delay. RTT 10 to 45 minutes when you have direct line of sight. Earth to Moon, one-way delay, kind of less than 2 seconds. In the overall architecture, the key problem is, or more difficult problem is the interruptions of communications of links. Next slide. So why that happen? It's easy. Because the different parties involved do not have a direct line of sight. So example 1, I cannot from Earth communicate with the orbiter because the orbiter is behind Mars. And here I can communicate with the orbiter, but the orbiter cannot communicate with the rover because the rover is on the other side of Mars. You got it? And so planets and moons are orbiting, orbiters are orbiting. So we have those kinds of non-continuous communications that are typically planned between different peers. Well, you don't have that problem if you are on Earth because like Starlink has so many satellites around Earth that you have kind of global connectivity. Mars and Moon are similar and different. Similar because they are far, therefore it costs a lot of money to send something there. Similar or different because Moon studies says it's like probably 7 or 8 around, less than 10 relays or orbiters would be able to cover the whole Moon. And it's cheaper to send, spacecraft to Moon than to Mars. But yesterday, we just got news from SpaceX that in a study to NASA, so don't be too excited. Yeah, it's just a study. They proposed to NASA to build, roughly a Starlink over Mars. And so it's a study, and to improve the bandwidth between Mars and Earth using laser communications. Relays, so orbiters, so orbiters, relays, forwarders are roughly the same. They may be routers, layer 3 routers or not, depends. Because of this situation, need to store frames or packets until the next up becomes reachable. This is currently done at layer 2. Example, all the 5 orbiters around Mars are actually storing frames. Essentially, because those relays were not sent for being relays, they were actually sent for example, MRO, Mars Reconnaissance Orbiter, was there for taking pictures of Mars at different wavelengths, right? But they were repurposed to be relays later. So their functionality is pretty limited. So the way people in the space describe these relays as their forwarding function is they forward bags of bits. They don't even know what a frame is. So it's very, very limited in terms of functionality, in terms of what we currently do with our layer 2 IEEE or stuff. And it's all point-to-point links. I'm coming back on this, but there's no broadcast domain there. Next. Give you some rough ideas. We did a study with GPL on Mars communication windows. I presented this in more length at the Deep Space side meeting on Monday, so you could refer to the more details there. So it's a data set of 3 months of communication window spans from the MAROS database. MAROS is the kind of project that is kind of the broker of all the communication windows. So Earth to Mars, Mars to orbiters, orbiters to rovers, and all that stuff. Next one. Skipping that, we knitted kind of the round trip paths from Earth to Mars to rover to orbiter to Earth. Uplink communication windows from average is 2.5 hours, could be 10 minutes or 10 hours. Downlink, kind of similar, and a lot of variations. Next slide. Best RTT, which is kind of approximated using some heuristics, and again, I'm not going to detail, but so the RTT from Earth, Mars to Earth, average of 16 hours, minimum is 37 minutes when everything is line of sight, and maximum could be 7 days. Because MAVEN, one of the orbiter, is actually in an elliptical orbit. So typically, the pass is 3 days, but in the data set I had, there was, one pass that was skipped for, because it's space. So it's like 7 days before the next pass. Next slide. Different RTT than what we're used to. Orbiter holding time. So the time that data storage, the bag of bits that was put, average is 15 hours. So minimum is 0 because again, if everything is line of sight, then you don't need to store any data. Maximum, you got it, 7 days. Next slide. So this is kind of our stack. You may be interested on the left side, which is CCSDS space links. I'll come back on this. IP TCP doesn't work well. We're looking at UDP Quick and CoAP. There's someone in the room that has been presenting how to use CoAP in space, and all those various. One other thing I could say is that on surface and orbit of the celestial bodies, so Moon and Mars, for example, the current plan and very large consensus is we will be running 5G and 802 star kind of networks. So on the surface of the Moon and orbit, it will be like Earth, right? Same kind of technologies, so routers and multiple providers, peering, and all standard stuff in some ways. They may have a little bit more problems to deploy this because there's dust and all that stuff. But from our perspective, it's business as usual. Next slide.
If I may, now maybe people realize why we're here, right? If you look at this stack and the kind of stack we operate in IoT, and in particular, if you just switch, for instance, CCSDS with LoRaWAN, you realize that it's pretty much this kind of stacks that we are using. So sorry for the interrupt, and you have 5 more minutes.
So this is essentially what I was trying to say, is that there will be multiple stuff on Moon or Mars, but roughly speaking, on a functional representation, you'll have a network on Earth, a network on the celestial body, and then relays in between, and sometimes direct communications between the two. For example, the oldest rovers on Mars need to go through relays, but the newest one, like Perseverance, is actually, or M20, is actually receiving directly from Earth, direct link to the rover from the uplink, but is using relays downlink. So it's kind of a mixed environment. Next. Yeah. Well, yeah, before. So these are all essentially point-to-point links. So when Laurent came to me, it's like, oh, well, I was looking for a header compression solution, and yeah, shit. So makes complete sense, because bandwidth in space is very precious and limited. So we must do this. Yes, next slide. So link characteristics, questions that have been asked. IP is encapsulated in CCSDS frames. They have multiple layer 2 protocols, but they have a generic encapsulation protocol in between, like a shim. So from our perspective of IP, we don't need to know all the different kind of layer 2. There's an encapsulation shim in between. Point to point, bandwidth is very precious. It really depends. Currently, like Mars uplink, Earth to Mars is in kilobit per second, and Mars to Earth is megabit per second. Why is because they essentially only send commands, like this looks like assembly language, like F32 space 5 space 3 means rover, move your camera or something. So very low bandwidth, and then they send back essentially telemetry, sensor data, image, stuff like that. Optical lasers that test have, near Earth or, going to the moon will be, have been done with 100 megabit per second, maybe gigabit per second. So you see that, but that's mostly future, short time future in some ways. Last, you need to be very careful about if you're talking about the bit rate, error rate or the frame error rate, because they do affect a lot in their link layers. They do a pipeline of codecs, and I've been trying to find the data papers on this, and I talked to roughly 3 people in this field. The chair of the CCSDS link working group. He's a European Space Agency operations, and the guy who is designing the radios for NASA. And I was not able to get exact number. Do you look at those numbers? And the operations guy say, no, it just works. It's kind of a simplistic version of it, but roughly that is what it is. So the bit error rate may be larger, but because they are heavily using FEC, and because the commands that they send in space are so important, right? It's like commanding a robot, so you don't want to have those data mixed up. So they actually have so I was asking about numbers, or can you show me a paper or something? The only thing I got from two of them, it's like they estimate as 10 to the minus 12 or better for the frame error rate, but not the bit error rate. Next slide. I think I'm done.
Yes, I have a question, if you don't mind, or comment. Again, we realize why we're here because, as Kirsten mentioned earlier, one of the reasons for FEC is when you have a very long round trip. So it's clearly something that's of interest. They already do it within frame, but as we discussed earlier, the interruption of communication might be longer than one frame, meaning that something which interleaves frames and enables frames, FEC between frames like we do with our fragments is an additional value. And then you also mentioned, Mark, that there will be a constellation of orbiters at some point, meaning that there will be multiple paths around the planet to go back to Earth through different sets of orbiters via other orbiters when they are meshed. And that's when this other discussion about using FEC over a graph starts making a lot of sense to me, at least.
Next slide. So our layers is similar to the graph, the drawing I just showed. So IP transport, UDP quick, TCP not very good for Mars, could be for Moon. Maybe other transports, but that's their current focus is quick. Current applications in space are typically currently limited to command, file transfer, and video streaming. Not really in the sense that there's some time between the sender and the receiver, but I'll ensure you that for Moon, people will be creative. Next slide. So deep space, I was asked for the status of the possible deep space IP working group. We had a buff yesterday, questions asked during the meeting, numbers from my memory. I was doing this yesterday. Minutes are not yet out, but questions were, are we working only for Moon or also include Mars? And Mars was like 2/3 of the answers, and want to work on it was like something like 95% of people. Again, I was thinking of not writing this because I didn't look at the notes, but that's out of memory. To me, it was like large support. We need to iron out the charter, and we may need to change the working group name. It's the ISG want. Sorry? Whatever.
Call it 9.
Yeah. So if the ISG is willing to have a working group on this topic. I think that's my last slide there. Yeah. So if you want more information, what we're doing, mailing list, our current group pages, which has all the archives of site meetings, presentations, link to documents, recordings, all that stuff. The second one.
So maybe just a short question. Thank you very much, and thank you for being here.
What you were looking for?
Okay, exactly, perfect. So yesterday in the discussion in the charter, it was a lot focused on quick.
Mm-hmm.
Does that exclude co-op in some way?
Good question.
I didn't want to ask it yesterday because, like,
we have that. So in some ways, we're looking at the whole IP stack, right? For example, I didn't talk, and I was kind of forced to not talk about network management. We need to manage this network, right? So there's various pieces around, right? That we should, in my book, we should look at. Yeah, right. Does that work in this environment, right? But the overall direction we got and is like narrow focus for the purpose of not trying to boil the ocean. So to me, co-op makes a lot of sense being discussed, but let's start with something smaller in scope, narrow, and then because there are many topics around that, for example, time synchronization, does NTP works in this environment? Yeah, I've been looking at this problem for a while, talking to NTP experts. So there's a good sign, but, and the idea here is that we would be only doing profiles, right? We do not intend to make changes to protocols. Protocols will be, in CoAP or in whatever. We're doing profiles, right? So how do you, have this protocol working in deep space? Do you need to change timers or, something in it? So.
Okay. Thank you very much, Rudy. And we're moving on to the presentation on networks susceptible to disruptions, which was zero energy devices, but now it covers as well deep space.
And Rodrigo will be presenting, so it's a change versus the original agenda. And Rodrigo, I think you wanted to get the hand, so now you should have it. So please feel free to start.
Can you hear me?
Yes, we can.
Okay, thanks.
Yeah, is it okay? Normally you have control of the slides. But
yes, it's my
loading.
first my first presentation because I don't know control the presentation. I select my slide, but the slide is in the list. Yes. Give me a second. I select the. Okay. Can you see?
Yes, it's there.
Okay, perfect. Okay.
So you can start whatever you want, and you have 10 minutes.
Okay. Well, good morning, everyone. Thank you for giving me this space in today's agenda. First, let me introduce myself. I am Rodrigo Muñoz from University of Chile, and I will show you our progress on the draft related to using SCHC in scenarios with disruptions. At this point, the draft is in an initial version, and this presentation shows the features we want to include in the new version. The current version of the draft focuses only on problems caused by disruption in SCHC communication for zero energy device or Z devices. Specifically, it includes several network topology design for zero energy device that work with cellular networks, in particular 3GPP networks. The document introduces a new network element called SCHC proxy, and we will better define its general functioning in the next version of the document, but we believe that it should be considered for inclusion in the SCHC architecture. The first version of draft does not define the message flow when the solution uses the SCHC proxy. However, it is important to note that the draft does indicate that the SCHC proxy will maintain the state of the SCHC sessions. The figure in this slide show the position of the SCHC proxy concerning the SCHC gateway and the SCHC end device. The figure also indicates that the link between the SCHC proxy and the zero energy device has interruptions, and the other links have no disruption. As we will see later, interruption can occur on any link. Okay. The study for disruption in zero energy devices gave us the impetus to examine other scenarios with disruptions in the communication. Thus, an example of a scenario with disruption is ship communication via LEO satellites. In LEO satellites communication, when the link is direct between the end node and the satellite, we say they are in a direct to satellite IoT architecture or DTS IoT solution. In DTS IoT, there is no need for a terrestrial LP1 gateway, such as a radio gateway for LoRaWAN or an eNode B for narrowband IoT. But in DTS IoT, the LP1 gateway is integrated into the satellite. For the operation of an LEO satellite, we define two time windows. The first window is called the visibility window or visibility time. This window is when a device on the ground can communicate with a satellite. Typical values for the visibility window range from 1 minute or 10 minutes, depending on parameters such as constellation density, satellite orbit height, or observer latitude and elevation angle. The other window is the pass-to-pass window or revisit time. This window is the time between the end of a visibility window and the beginning of the next visibility window for the same device on the ground. The figure shows a typical communication between an end device and a server on the ground passing through a LEO satellite. In DTS IoT, the link between the end device and the LEO satellite typically use LP1 access technology. And the LEO satellite may also experience disruption to the ground station. From the point of view of SCHC architecture, the SCHC node is in the end device, and the SCHC gateway is installed on a server on the ground. In most SCHC profile, for example, LoRaWAN or narrowband IoT, fragmentation in the uplink use a error mode. In this way, in DTS IoT, the uplink transmission of a SCHC window can be divided into three phases. In phase one, the end device sends the tile directly to the LEO satellite. The satellite stores them for delivery to the SCHC gateway in the next phase, in phase two. In phase two, the LEO satellite delivers the tile to the SCHC gateway, and the SCHC gateway responds with a SCHC ACK message indicating which tiles are missing. In phase three, the LEO satellite delivers the SCHC ACK message to the end device. At this point, the end device decides whether to send the transmission of a new window or retransmit the missing tiles. However, it is important to note that sending a SCHC window or a SCHC retransmission window follow the same three steps explained above. When the loss of tile increase, the number of retransmission window increase. As a consequence, the transfer time of a SCHC packet also increase. Based on this problem, our solution considers the LEO satellite as a SCHC proxy. Therefore, the SCHC proxy will have two features to improve SCHC performance. First, in the link between the end device and the LEO satellite, the proxy will use local acknowledgement to accelerate the retransmission. And second feature is the proxy will use local retransmission in the link between the SCHC proxy and the SCHC gateway. The figure showed the transmission of three SCHC regular fragment message, and each SCHC regular fragment message carries one tile. The SCHC regular fragment message carrying tile number 2 needs to be recovered in the example. In a normal situation, the end device will have to wait for the complete transmission cycle of a SCHC window to know which tile were lost. With the local acknowledgement, the CHIC proxy informs the end device which tile are missing, so they can be retransmitted in the same phase or visibility window. Then this feature will reduce the transfer time of a CHIC packet.
Rodrigo, we will ask you to accelerate a bit.
Sorry, in this slide, I want other slide. In this slide, the figure showed the loss of a tile between the CHIC proxy and the CHIC gateway. In this case, the CHIC ACK message indicate the loss of the message is not retransmitted to the end device. The CHIC proxy stores a copy of the lost tile, allowing it to be forwarded directly to the CHIC gateway. This again accelerates the successful transmission of a CHIC window by avoiding subsequent retransmission windows. This has been a summary of the new scenario that has been added to the draft. Again, thank you very much for your attention, and I look forward to your question.
Thank you very much, Rodrigo. I just have a very short question, and then we can move to the next one. Do you have a specific LEO constellation in mind, a specific technology for this use case?
No, I don't use. For example, I use LoRaWAN, but the define of CHIC proxy is not considered the LP1 technology. The definition is the same for LoRaWAN or Narrowband IoT.
Okay, I mean, because there are a couple of them, and probably it could be nice to have like one specific in mind, so that to see the applicability. Like I know that Kineis, they have something like this, but they are not the only ones, right? That do stuff like this. Okay, thank you very much. Really great. So we are going to move on. Thank you very much, Rodrigo. And now it is the presentation of Mariam. Mariam, can you?
Yes. Hello.
Yes, I can move the slides for you. You can just so we have between 10 and 15 minutes. 10 minutes if we can make it, that would be great. So yes, you can tell me when to change the slides.
Okay, awesome. Thank you.
So you can normally you have the slides already, so you can start.
Okay, yeah, just a moment.
Okay, whenever you're ready.
Okay, so yes, we can start. So I am Mariam Hatami, a PhD student at Concordia University. I'm presenting my master's thesis work about secure and autonomic framework for CHIC context management in LoRaWAN IPv6 network. So next slide, please. To introduce you with the problem, the thing is that there are many IoT devices which are connected to their applications using simplified communication protocols with minimal security. So there is an increasing need to merge the IoT constraint islands into the general internet, and this is becoming more feasible as IoT device capabilities have increased. So communication protocols targeted for the IoT space often have very small MTUs, and IPv6 addresses are quite large. So in this case, as we know, CHIC comes to provide a methodology to reduce the size of the IP header and provide the necessary fragmentation. So this communication between the IoT constrained devices with the larger network like the IPv6 base are possible. Next slide, please. So the goal here is to show how we can create a management plane between these two starting point and the end point. And we want to demonstrate that we can combine CHC and ANIMA, which comes from the ANIMA working group. It meets the goal and in a feasible way that does not take too much time for the setup. So the approach that we did was that I assumed an initial rule set for the CHC, a new rule for that onboarding mechanism, which is the CHC 0 rule, as I defined. And then I assumed that using the ANIMA required certificates, and then we calculated the time required for all the ANIMA onboarding message exchanges using the MATLAB simulation. Next slide, please. So here is the protocol stack and the architecture that you can see. So on the left side, you can see the constraint end device. And on the right side, it continues with the components of the ANIMA onboarding solution. And both of the ANIMA mechanisms used are Brusky and Cbrusky, which are the onboarding solutions. So here, as you can see, between the LoRaWAN layer and the IPv6 or ICMPv6 layers, we need a compression where we defined a CHC 0. Next slide, please. So here you can see that this is the complete architecture that I provided. Having the both CHC 0 compression, decompression, and fragmentation reassembly inside this protocol stack. And the next slide, please. So yes, here is the CHC 0 example rule set that I defined. So having all the information from Brusky and the architecture that we have, like the number of hop limits or the next header or the address of the the source address of the device and the prefix and the UDP ports and so on. Using all the information that we had, I tried to store all of them, and I reduced all the messages passed for this onboarding solution. Next slide, please. So here you can see all the messages passed for this ANIMA onboarding solution with compressed headers. You can see that the headers has been compressed. And in the next slide, I show that how it shows the timing as well. Yes, here you can see that by calculating on the MATLAB simulation, I simulated this network architecture and the onboarding time on both the worst case and best case as for LoRaWAN. As an example for the constraint device is calculated. For example, for the best case, which is the spreading factor 7 in the LoRaWAN device, it is less than an hour. And in the worst case scenario, it took around 5 hours. So this shows that this is feasible. Next slide, please. So in the conclusion, we figure out that the IoT device is securely managed in this way. And now, after that setup, we are possible to update the CHC rules in a secure and autonomic way without any human intervention. And we can also update the basic softwares and application softwares while ensuring the identity of the device itself. And now we are possible to attach a globally routable IPv6 address if necessary, all in an autonomic and secure way. And next slide, please. So here is the next step to implement on a real testbed and with this simulation we had, and also measure the energy efficiency of the device as well. and continue the work with the CHIC context update and show how it works. And next slide, please. Thank you so much for hearing this presentation. And if you had any questions or comments, I'll be so happy to hear that. Thank you so much.
Hello, Miriam. Yes, this is Pascal, Chair. Personally, I really love this work, and I'm just curious if you have the intention to continue with the IETF and an internet draft in this working group, which I would really welcome.
That's great. Thank you. Yes.
I mean, do you know our process is to write documents in the IETF form, and do you intend to continue working with us and write this sort of document?
Yes, yes, sure. That would be my pleasure to continue this.
Yes, thank you very much for your presentation. It was very, very interesting. I have two questions. In your architecture, you show... Sorry? Okay.
Yes.
So in the architecture, you show ICMPv6. So do you need in the future to compress also ICMPv6 or not?
Yes, actually, for the constrained devices, we need to compress the ICMPv6 as well.
Okay, yeah, that's a. The other question was about Anima. I don't know the format of Anima messages, but can we apply SCHC on them too?
The Anima messages, actually, yeah, the formats and the protocol they use are like as I showed in the architecture, and they are HTTP, TCP, and IPv6 and ICMPv6, and these are the protocols that we had. Actually, these are all the headers that we can apply the CHC compression on them. So I just applied the compression mechanism on them. If we have more compression defined in future, so we can apply more and make it more compressed even.
Okay, perfect. Thank you.
Thank you.
Hello, Antoine Tressancourt. I had a question regarding Brewski because I'm not really familiar with it. From the abstract of the draft, it seems that it's based on having a secret in and you share it and you bootstrap to have a secure communication with the controller in Anima. The secret, it's present at manufacturing of the device. How is this initial secret put in the device?
Excuse me, can you repeat the last part? I think that I didn't get it.
So how is the initial secret provisioned in the device, and what would you need to make sure that in the architecture that the controller contacts the proper device in Brewski?
Yes, exactly. The security measurements are actually stored inside the device, and it uses the manufacturer, and also the registrar is connected to a certificate authority. So it is using the third trusted party, using the PKIX mechanism to do all of these authentication and the security protocols.
Okay, thank you.
We're getting late, so we'll lock the queue after ESCO.
Esco here. So I just want to say about Brewski, yeah, I think the initial secret can be put into the device in many ways. So it's typically done by the vendor in some way. It's an IDEF ID certificate actually for Brewski with private key.
Thank you, ESCO. And with this, we'll move to our last presentation, and I think it's going to be Anna. So that's the flow compression, which is pretty much a spin-off of the ICMP work, where we want to create more action types than just the reply by the gateway or the the ICMP presentation, that the echo basically by the device or by the proxy in front of it. So this is kind of generalizing this concept. And now the floor is yours.
Thank you. Hello. The idea, thank you very much for this slot. The idea is to discuss about a new parameter that we can add in the rule in order as make an action. As Laurent explained in his presentation, he talked about the proxy ping and how he can respond to this ping using something in the rule. So in this work, we are trying to use SCHC to compress a flow. So next slide, please. As you know, SCHC compress packets independently. So it doesn't keep a memory, it does not update the context. So we don't have the history of what we have been done. So each packet is independent and you can use any rule in the set of rules. Next slide, please. And when you are doing a SCHC compression flow, so the definition in the headers of the field headers in the header, some of them define a flow. Some of them are dependent of what has been sent before, as a sequence number or timestamp. So we need to, if we want to compress, for example, TCP or RTP or any protocol that produce a flow, we are looking for a solution to compress them. So we think that we can optimize SCHC compression as has been defined in 8724 by using the access control draft to update the evolution of the target value, the young data model management to make the changes in the field, and of course all this needs to be linked to something in the rule. So we create something that is an action in the rule that for in our case for flows we call it derived rules. Next slide, please. So I explain quickly SCHC. You have the packets, you receive it when you arrive to the SCHC. In the set of rules, you choose the rule that gives you the best results, and then you compress the packet. And you do that for each packet independently. Next slide. So when you have all the packets, each one will be compressed with may be compressed with a different rule or with the same, but you don't know. You don't know that you have already used rule 3 or your 2. You compress your packet independently. Next slide. And when we want to go towards the flow compression, we say that, for example, the packet n will be recompressed with rule 2, and then n, the packet n plus 1, that is the next packet in the flow. Well, it might be compressed with another rule, but as it's in the flow, the base of the header fields are already in rule 2. So if you don't want to have a lot of rules in your set of rules, because you will need a rule per packet at least. So the idea is that you make an indication in your rule 2 that this rule may have an action, and in our case is derived action, to create a new rule when the next packet will arrive, because you will have the same field IDs, but they will be updated by the young data model. Next slide, please. And so this new derivable action will keep the information of the history of the flow fields, and will manage the creation and erasing and update the derived rules. So next slide, please. The idea is to discuss about this new item in the rule that we call action. Next slide. And we define action as an indication in the rule to perform some operations. So in our case, for flows is a derived rule. Don't create a new rule with the updated information. And for example, proxy that Laurent present was answering the ping. So we want to know if this idea you agree, or if we can include this in the architecture, and what do you think about that? Thank you. That's my last. Next slide is my last. Yeah.
Okay, just one precision. I think it will be very useful for quick compression, because at the beginning we just focus now on outer header of quick, so IP, UDP, and maybe some fields of quick that are not encrypted. So at the beginning you have a very generic packet that do a very low compression of IP, UDP. But once you have learned the IP address, the flow label, the UDP ports, then you can create a specific rules that will do more compressed version, or we can do more compression, and this way we can enhance the compression for this flow.
How do you synchronize the two sides?
So we have CoreConf, and so the action of derivable means that we create a new rule and we set up using CoreConf management on the other side, and then we use it until, for example, if the rule is not used for 1 minute, then it's removed. And if it's removed, then we go back to the generic rule.
So you have to be transactional, make sure that both ends are kept in sync.
Yeah, we need to, that's the fundamental of SCHC, is that we know that we have the same set of rules in both sides.
Understand? Yes.
Yeah, I probably had the same question, just with different words. So there is some state management going on here, and I'm trying to understand. I mean, we have this 40-year history of header compression. We understand a few things about the state management there, and I'm trying to understand how this state management fits with existing state management schemes we have had, and that we know well what the advantages and disadvantages are. So I would really come into this from the point of view of state management. Now, having an action that is stateless, like answering that ping, that's
Easier.
easy. And I think it's good to have that. Yeah, I think we need to have an architecture for how to manage these states. And just saying we can use CoreConf. Yeah, that may be the implementation of that architecture, but I think we still have to look at this at the architecture level.
Yes, and that's a bigger change to the architecture than just defining action. I mean, the big, and we need it anyway. We've known forever that we need this thing.
Just to answer Carsten, I think the main difference is that we are not changing the compression phase. It means that we have a packet that arrives, there is a set of rules in front of it, and we do compression packet per packet. And what we do is just by management adding new rules, but we don't have a flow at the compression level. We just create a rule that fit more to some characteristic of packets. And so we still continue, we don't change the SCHC compression mechanism. What we add is just a mechanism to exchange rules.
But you depend on this state management that Carsten was talking about.
Yeah.
And for me, that's the bigger change in the architecture, is to describe how we do that, exactly as Carsten has been saying. And then, yes, what you're saying makes sense.
So if I remember right, the S in SCHC stands for static. So we're now doing a DIC.
Yes, maybe Anna wants to answer. The static means that when you send a packet, you don't change the context. So it's static context. It's not, and that's all. And here, what we do is we have a synchronized context, if you prefer. So we keep SCHC in that case. And so we add some or remove some rules in the set of rules.
So okay, after Karsten, I have something to add.
Yeah, so this is exactly the question that Pascal asked. And, so when we did ROC, our work was about how to properly synchronize that context. And many ways of doing it and all the advantages.
Yes. So thank you for the discussion. And well, I'm coming back maybe to the original presentation, which was okay. Do we need something like action? So of course, basically, I feel that in the presentation there are 2 points. One is okay. There is this concept of derived rules that you can use something to derive existing rules, and then there is the point of okay, do we need something like an action that, like a procedure or a function that is called whenever a compression rule is selected, right? And maybe we need to specify when that happens. Is it before? Is it right after the selection? Is it upon the after the compression is applied? You know, probably there are different points where the action can be executed. So maybe that's a question also for the working group. Do you think that this is an item we should be working on? So okay, and I'm going to use the show of hands, and Antoine, you can come to the mic by the time I'm putting the show of hands.
Just while we do the show of hands, in fact, hearing the discussions about the rules and the exchange of context, it reminded me of a very old RFC capsule protocol, like end of 90s, I think, for active networks. And more recent work was protocol plugins that was introduced for BGP. It's a research article. Randy Bush is among the authors, and in fact, this was meant to define a way to pass the understanding of a BGP extension where the router couldn't understand the extension. So it was very fitting in the context. So.
We need to have this discussion on mailing list, how we do state synchronization, and then have the architecture reflect that. So please follow, and Karsten also, please follow the mailing list, and let's see what words we can find for the architecture, something high level enough that can then be implemented by drafts.
Okay, so the show of hands is running. Maybe we'll leave it running for, oh, Eric, yes, coming to the mic.
So the show one is perfect. Eric Ving, the show one is perfect. We can do it. Just to be clear, we will need the chair to check whether it's fit the charter. Right.
Are we done with the show of hands? Can we stop it?
Yes, so there are, okay. So yes, like the majority of the people, 12 votes say yes, there is something we should be doing there. There are 2 votes no, and 2 with no opinion. So definitely we need to look if that's in our charter, and we need to go to the mailing list anyway. So with this, I think that we have finished our on time. We're done. Thank you very much. Thank you for coming and staying until Friday. Carlos wants to say something.
Yeah. So is it AOB already?
Yes.
Okay, thank you.
AOB, yes.
Quick comment. Basically, well, first of all, thanks to the authors of the SCHC architecture draft for all the work put into it and the discussions ongoing. So now there are several documents that depend somewhat on it in this working group and also in other working groups. So yeah, it would indeed be great to have a 03 somewhat, well, whenever time permits.
Yeah.
Thank you.
Thank you. Point noted, Carlos. So thank you very much to the minute takers. Thanks, ESCO. Thanks to everyone that helped with this. And with this, we wish you have a pleasant day. Bye.
So the notes ended up in 2 different places, so there were multiple people taking notes. So
okay.
a bunch of notes.